Okay, hello everyone. So today we will be discussing about the moving coil galvanometer. So as you know very well that galvanometer measures current through it. Okay, so it deflects when a small current passes through it. Now we have already studied the tangent galvanometer before. Now we'll be studying moving coil galvanometer. So there is a very strong magnetic field involved here. So here the shape is like this. This this is the north pole and uh, this is the south pole of a very strong magnet, and see, these are the lines like this, and as you can see that the magnets are like this circular in shape, and here in between this is a soft iron core. This is a soft iron core. I will draw again in details this thing, and uh, wrapped on the soft iron core is a coil like this. And about this thing is hanging from ceiling. I mean, this soft iron core is hanging from a ceiling. Now this is a hairspring. It is hanging through a hairspring. So this little thing is known as the hairspring. As you can see, this one. Hairspring of torsion constant K. Hairspring of torsion constant K. That means if for this hairspring, I am drawing it below, like see, if it rotates by angle theta, then it will give a resistive torque K theta. So if the hairspring rotates by theta, it will give a resistive torque. Okay. So and this thing is this red thing is known as red thing is the coil. So this is a coil of n turns, and area of the coil is A, and this area A. So by area A I mean this thing. See, it's actually a rectangle. This coil is actually a rectangle. So you can tell that, okay, as it's a rectangle, this thing is the diameter of the cylinder, and this thing is the length of the cylinder, diameter of the length, and this is area of the coil A. So it's d multiplied by L. Okay. Now this thing is the soft iron core. Soft iron core. Now, why this soft iron core is required? It attracts the magnetic field towards it. Now I'll be showing the top view of this thing. See. North pole of the magnet, south pole of the magnet, and there this is a soft iron core, and this is the coil. This red one is the coil. This is as you can view from the top. And let me draw the magnetic field lines. The magnetic field lines are like this. Okay. So what happens actually, as you see, whatever configuration there be of this coil, suppose this coil has rotated to a position here, then also if you look at the magnetic field, they are like this. And suppose the coil has rotated here, say here, coil has rotated to this position, then also the magnetic fields are like this. So at all positions, you see the coil, if you see, this is the magnetic moment of the coil, this magnetic moment of the coil M, right? And this is a magnetic field, the strong magnetic field due to this circular shaped magnet. Okay, so at all positions of the coil, page this diagram, right? So it's, so M and B are always perpendicular to each other. So here okay, so for all positions of the coil, what happens, this M is perpendicular to B, that you can see from the okay. So that means the torque, so the torque, therefore for all positions of the coil, for all positions of the coil, the torque, obviously the magnetic torque is MB sine of 90 degree, right? MB sine of 90 degree, because it is always 90 degree for whatever. This is the coil, again I am drawing, this is the coil, this is the magnetic moment of the coil, magnetic moment vector of the coil, and this is the magnetic field vector of the coil. It happens to be 90 degree for all positions. Wherever the coil rotates, it makes 90 degree. So that means it is M into B. Now suppose this N is number of turns of the coil, and A is area of coil. So therefore, and say I is current in the coil, so therefore this magnetic moment is equal to Ni into A. So the torque, magnetic torque, is equal to Nia multiplied by B. Now, so the coil experiences a torque, rotates, and after that it comes to equilibrium. When does it come to equilibrium? When it is opposed by exactly equal torque, right? So it is opposed by exactly equal torque which it gets from the spring. So there M cross B, there is a coil M and B. So this is the torque, MB torque, and the hairspring that also rotates. So due to that the torque is this way. So that is K into theta, because this K is the torsion constant of the spring, I have told before. So these two are equal. That means we can write this MB or NIAB is equal to K times theta. So therefore I is equal to K by N, I is equal to K by NAB times theta. So this is how you measure the current, by measuring the deflection, right? So as you know that with this with this coil or this, okay, so this is the constant of the galvanometer. I am drawing the diagram shortly after this. This is the constant of the galvanometer. Okay. Now, see, as you can see that with this coil there is attached, with this soft iron core there is a pointer and a dial here. So there are graduations on this circular scale. So as it rotates by theta, so there is reading. So there is a reading of theta here, right? Now, we'll talk about sensitivity of a galvanometer. Now, this is so what we have got, theta is equal to, so what is I equal to? I is equal to K divided by NAB times theta. Okay, so this theta divided by I is equal to, theta divided by I is NAB divided by K. This is known as the current sensitivity. The current sensitivity of the galvanometer. Now, if V is the potential difference, across terminals of this galvanometer, that is V is equal to I multiplied by R. This R is the resistance of the galvanometer, right? Resistance of galvanometer. Then this term theta divided by V, that means theta for unit voltage. This is known as the voltage sensitivity. Of the galvanometer. So this was our brief study on moving coil galvanometer, and we have learned before already tangent galvanometer.